In the today's class, we will take up the concept of series resonant circuit, which is basically the AC circuit containing resistance, capacitance, and inductor in series. So three components are connected in series. So that is called as series resonance circuit. So what is resonance? Other things we'll study in detail. So consider a resistor of resistance R, a capacitor of capacitance C, and inductor of inductance L are connected in series with AC voltage source of V equal to V naught sin omega t. So we'll connect a circuit containing a resistor, inductor, and a capacitance in series, RLC, connected in series. This series combination is connected to the AC source, and AC is having the voltage V equal to V naught into e to the power j omega t. So in terms of sinusoidal voltage, V equal to V naught into sine of omega t, or you can represent that in complex number representation by V is equal to V naught into e to the power j omega t. Now already we know that inductive reactance XL introduces phase difference of plus pi by 2. Already I have told you the inductor will introduce the phase difference of plus pi by 2, and capacitive reactance XC introduces the phase difference of minus pi by 2 with respect to the resistance R, because voltage and current will be in phase with respect to the resistance. In case of inductor, the phase difference of plus pi by 2 is observed. With respect to the capacitor, the phase difference of minus pi by 2 is observed. So therefore, the inductive reactance and capacitive reactance can be represented using J operator. So plus pi by 2 represents plus J operator, minus pi by 2 represents minus pi by 2 phase difference. Okay, minus J means minus pi by 2, plus J means plus pi by 2 phase difference. So using that concept, definitely the resistance, effective resistance of the resistor is R, whereas inductive reactance can be written with phase difference, that is plus J omega L, where omega L is the inductive reactance, plus J is introduced to represent the phase difference. So phase difference between this resistance and omega L is plus J or plus pi by 2. Similarly, the capacitive reactance is minus J into 1 by omega C, where capacitive reactance is 1 by omega C. Already you have seen in the previous class. Minus J represents the phase difference of minus pi by 2. So basically, inductor introduces plus pi by 2 phase difference. Capacitor represents the minus pi by 2 phase difference. That is represented in terms of the plus J and minus J operators. Okay. Now apply the KVL to this particular loop, KVL to the circuit, that is Kirchhoff's voltage law. The effective voltage applied to the circuit, that is equal to current into effective resistance. So current is I, that is the instantaneous current I, into effective resistance is R plus J omega L minus J into 1 by omega C. Remember, they are connected in series. Therefore, the effective voltage V is equal to current into the effective resistance. Okay, effective resistance is total resistance of the circuit, that is given by R plus J omega L minus J into 1 by omega C. Finally, we have to find out the expression for current I. Okay, expression for current we have to find. So here, voltage applied to the circuit is V equal to V naught into e to the power j omega t. That is the effective AC voltage applied. That is equal to current into the effective resistance. So I have kept it as it is. I into resistance R plus J into omega L minus 1 by omega C. Here J is taken as a common factor. Omega L minus 1 by omega C will be retained in the inside the bracket. So here I is the instantaneous current through the circuit. I is the instantaneous current through the circuit. We have to find the expression for this I. Therefore, the current through the circuit I is equal to V naught into e to the power j omega t divided by the total resistance. Total resistance. Voltage by resistance. It is simple Ohm's law. Current I equal to voltage by total resistance. The voltage is V naught into e to the power j omega t and resistance is R plus j into omega L minus 1 by omega c. That is the expression for current. So next we'll try to express this current in terms of phase. Okay, we have to find the phase difference between voltage and current. So for that, what we'll do, we'll multiply this equation by the complex conjugate of the denominator. So you might have studied the solution for the complex number which is in the denominator can be done by the method of multiplication and division of the term by the complex conjugate of the denominator. So here denominator is R plus j into omega L minus 1 by omega c. It is a complex number where R is the real part, omega L minus 1 by omega c is the imaginary part of this complex number. This V naught into e to the power j omega t, it is also complex number only. It is in terms of sine of omega t, cos of omega t, plus j sine omega t, where j is the complex number. Okay. What you can do, you can multiply this term by complex conjugate of the denominator. What do you mean by complex conjugate? Complex conjugate is obtained by interchanging the sign of the imaginary number. Okay. So sign of the imaginary number should be interchanged. If it is plus, then you have to make it minus. So multiply and divide by the same term. That is, you have to multiply the equation by complex conjugate, divide the equation by same number. So it is just multiplying by 1. It is just like multiplying by 1. So here I have multiplied R minus j into omega L minus 1 by omega c and divided by R minus j into omega L minus 1 by omega c. Now the denominator is of the form a plus b into a minus b. Just you look at the terms here. It is of the form a plus b into a minus b. Here a is R, b is j into omega L minus 1 by omega c. A plus b into a minus b is nothing but it is a square minus b square. That is the expression for the general expression identity. So here it can be rewritten as or you consider this term only, you neglect this only solution of this term will consider. The denominator will be r square plus omega L minus 1 by omega c the whole square. Here you will get a square minus b square. Here plus j minus j. If you multiply j and j, it will be j square. J square is minus 1. Already I have told you j is a complex number. J is equal to square root of minus 1. Therefore, j square is minus 1. Okay, definitely j square is minus 1. Minus into minus, it becomes plus. So numerator will be r minus j into omega L minus 1 by omega c. I have considered only this term. So solution of this term is considered first, then we will substitute that solution in this, the current equation. So here you will get the expression for this term will be r minus j into omega L minus 1 by omega c divided by r square plus omega L minus 1 by omega c the whole square. Okay. And I can represent this as alpha minus j beta. Okay, here I will represent this term as alpha minus j beta. What is alpha here? Alpha is r divided by this denominator. Beta is omega L minus 1 by omega c by this denominator, where alpha is r square divided by the denominator here, and beta is omega L minus 1 by omega c divided by the denominator of this equation. So we have got the complex number alpha minus j beta. Alpha and beta are defined using these two expressions. Okay. Now we will take up the value of alpha and beta are obtained here, and we will try to represent this alpha and beta in terms of some angle theta, because we have to find the phase angle between voltage and current. So for that, what we will do, we consider a trigonometric representation. We'll take up a triangle with angle theta. It is a right angled triangle having angle theta at as a one angle, and two sides are taken to be r and omega L minus 1 by omega c. Okay, the adjacent side is r, the opposite side of the angle theta is omega L minus 1 by omega c. If these two are having these magnitudes, then the hypotenuse of the triangle will be square root of r square plus omega L minus 1 by omega c the whole square. That is accordance with the Pythagoras theorem. Okay, so hypotenuse will be square root of square of sum of squares of two sides. So a square plus b square is equal to c square, and here we have obtained c, that is equal to square root of a square plus b square. So square root of r square plus omega L minus 1 by omega c the whole square. That is the hypotenuse. Okay, so therefore if you form such triangle, then tan theta will be equal to opposite by adjacent. So tan theta will be omega L minus 1 by omega c divided by r. Then what will be the cos theta? Cos theta is given by, it is given by adjacent by hypotenuse. Adjacent is r, hypotenuse is square root of r square plus omega L minus 1 by omega c the whole square. What is sin theta? Sin theta is given by opposite by hypotenuse. Opposite side is omega L minus 1 by omega c divided by the hypotenuse. Okay, now we have to express this alpha and beta in terms of this cos theta and sin theta. Just to look at these alpha and beta. So alpha is just like alpha is just like the cos theta divided by square root of this denominator, because square root of the denominator is here in cos theta expression. So this term can be rewritten as a square root of r square plus omega L minus 1 by omega c the whole square into square root of the same term again. Okay, so x can be rewritten as square root of x into square root of x. So is it right? So same thing we will do here, and alpha can be expressed in terms of cos theta and beta can be expressed in terms of sin theta, because numerators are same. Cos theta has the same numerator as that of alpha. Sin theta has the same numerator as that of beta. Therefore, we can express this in terms of theta by taking tan theta is equal to omega L minus 1 by omega c divided by r. We'll form this right angled triangle. Using that, you can express this alpha and beta in terms of theta. Therefore, this term, that is 1 by j plus r plus j into omega L minus 1 by omega c, can be rewritten as cos theta minus j sin theta divided by square root of r square plus omega L minus 1 by omega c the whole square. This is the expression for this term in the current expression. This cos theta minus j sin theta can be written as e to the power minus j theta, because we know that e to the power I theta is cos theta plus I sin theta. So cos theta minus j sin theta can be represented as e to the power minus j theta divided by r square plus omega L minus 1 by omega c the whole square. Now substitute this in the current equation. So expression for current is I equal to V by total resistance. Now we have proved that this total resistance, 1 by total resistance, is equal to e to the power j minus j theta divided by this denominator. Therefore, the expression for current I will be equal to V naught e to the power j omega t into e to the power minus j theta divided by square root of r square plus omega L minus 1 by omega c the whole square. That is the expression for current. Okay. So if you combine this exponential terms, you will get the expression for current as I equal to V naught into e to the power j into omega t minus theta. So e to the power j omega t into e to the power minus j theta is combined here. So you'll get e to the power j into omega t minus theta divided by square root of r square plus omega L minus 1 by omega c the whole square. Okay. Now look at the phase of the current. So current has the phase omega t minus theta. What is the phase of the voltage? Voltage has the phase omega t, because voltage is equal to V naught into e to the power j omega t. Therefore, voltage has the phase omega t and current has the phase equal to omega t minus theta. And here, I can write this current as V naught by effective resistance. Voltage by resistance is current. This term is dimensionless. Therefore, this must be having the dimension of current. So V naught by this denominator should be having the dimension of current, and I will call this term as I naught. So I naught is called as the peak current that can flow through the series resonant circuit. Okay. So here I naught is given by V naught divided by R square plus omega L minus 1 by omega C the whole square is called as peak current. So this term is replaced by I naught, and also this I naught can be written as V naught by Z, where Z is called as effective resistance of the circuit connected in the AC circuit. Okay, so components connected in the AC circuit. So I naught equal to V naught by Z. What is Z here? So Z is equal to square root of R square plus omega L minus 1 by omega C the whole square, and that is called as impedance of the series LCR circuit. This is going to be very important. Impedance means it is the effective resistance in the AC circuit. Okay, so in the AC circuit, we call the resistance as impedance. Impedance is nothing but resistance only, but it is the term used for AC circuits. Okay, and here I is written as I naught into e to the power j into omega t minus theta, and I is having the dimension of current. Okay, so therefore this must be V divided by resistance, voltage by resistance. Therefore this must be having the dimension of resistance, and we call this term as impedance of the circuit. Okay, question may be asked in the problem. You may have to find out the impedance of the circuit in series resonant circuit by giving the value of resistance, capacitance, and inductor. They may ask to find out the value of impedance. Okay, Z. And also you should remember Z is equal to V naught by I naught. That is simple expression. This can be rewritten in terms of V naught and I naught. Impedance of the circuit will be equal to peak voltage by peak current. That also gives the magnitude of impedance of the circuit. And already we have noted here the phase difference between voltage and current is theta, because voltage has phase of omega t, current is having the phase omega t minus theta. Therefore, the angle theta in the above equation represents the phase difference between voltage and current. So in series resonant circuit, what is the phase difference between voltage and current? That is given by theta is equal to tan inverse of omega L minus 1 by omega C divided by R, because we have taken tan theta equal to omega L minus 1 by omega C divided by R. Therefore, theta is equal to tan inverse of omega L minus 1 by omega C divided by R. So what we have derived here, we have derived the expression for current. We have derived the expression for impedance of the circuit, that is effective resistance. And what is the phase difference between voltage and current? So this is actually derivation corresponding to the properties of series resonant circuit. So if question is asked to derive the expression for current and impedance of the series resonant circuit, you have to do these all things. You have to obtain the expression for current, you have to obtain the expression for impedance, and you have to obtain the expression for the angle theta, where theta is the phase difference between voltage and current. Okay. And finally, we'll represent this in the phasor diagram. If omega L is greater than 1 by omega C, just you observe this equation. If this omega L is greater than 1 by omega C, then this numerator is positive. Therefore, theta will be positive. So value of theta depends on the magnitude of omega L and 1 by omega C. If omega L is greater, theta is positive. If 1 by omega C is greater, then theta will be negative. So value of inductor and capacitor decide the, the value of phase angle theta. So if theta is positive, then current lags behind the voltage by phase angle theta. If theta is positive means voltage is leading. Okay, so the phase difference between voltage and current is theta. So voltage is leading if omega L is greater than 1 by omega C. On the other hand, if omega L is less than 1 by omega C, then theta is going to be negative. Theta is negative if omega L is less than 1 by omega C. Okay. So then current leads the voltage by angle theta. Okay. So current is going in front of voltage. Okay. So current leads the voltage by phase angle theta. Then phase difference between current and voltage in the series LCR circuit is represented in the below figure. Here in this figure, VR represents the voltage across the resistance, VL represents the voltage across the inductor, VC represents the voltage across the capacitor. Okay, and here we'll take up the effective voltage between VL and VC. So they are opposite to one another. They are having the total phase difference of 180 degree because inductor introduces plus J phase difference. Capacitor introduces minus J phase difference. It introduces plus pi by 2 phase difference and capacitor introduces minus pi by 2 phase difference. Therefore, with respect to VR, VL is situated by 90 degree leading situation and VC is behind the VR by 90 degree. Okay, so VC and VR are having the angle 90 degree between them. VL and VR also have 90 degree phase difference between them. Now you find out what is the effective voltage that we have to find out. So first you find out what is the effective voltage between this vector VL and vector VC. These two vectors are opposite to one another. And this is the case where omega L is greater than 1 by omega C. Otherwise, this voltage is greater compared to the voltage across the capacitor. Okay, VL is greater than VC. Then VL is having this direction, VC is exactly opposite. Then effective resultant vector between this VL and VC will be equal to VL minus VC. And this is the vector representing the value of VL minus VC. Now you take the effective resultant vector between VR and this VL minus VC. And this is having this direction, VR is directed like this. Then you have to find out the resultant vector of two vectors by taking the law of parallelogram of vector. You draw one parallel line with respect to VL minus VC here. You draw one parallel line with respect to VR here. And the vector V0 represents the effective voltage of the series resonance circuit. And this is having the angle theta between this I0. That is, I0 is always directed along VR because the voltage and current will be in phase with respect to resistance. Therefore, I0 is always having the in phase relationship with the voltage across the resistor, whereas the effective voltage is having the phase difference of theta with respect to current here. So VR is having the phase omega t here plus theta. Omega t plus theta is going to be observed if VL is greater than VC. Similarly, if omega L is less than 1 by omega C, then current will lead the voltage by angle theta. So effective voltage will be V0 represented here. This is the effective voltage by taking the method of law of parallelogram of vectors. So VC minus VL you have to take because VC is greater than VL in this case. So voltage will lag behind the current by theta, angle theta. So voltage is here, current is here. So current is leading the voltage by angle theta. Here, current is lagging behind the voltage by angle theta. Here, voltage is here V0, I0 is behind the voltage. Okay, it is behind the voltage by angle theta. And here, current is leading the voltage by angle theta. So this is how you can represent the effective voltage and current in phasor diagram, and also it is possible to represent the phase difference between voltage and current using the phasor diagram. And this is about the information of series resonant circuit. So concept of resonance, we'll take up that in the next class. We'll stop here.